from the University of California Davis Cancer Center, and it's my pleasure to present an overview of our TRISH-funded project titled Effects of Mission-Relevant Doses of Solar Energetic Particle and Galactic Cosmic Ray Radiation on Human Hematopoietic and GI Systems. This is a program project that involves three institutions, UC Davis, the University of Arizona, and Wake Forest Institute for Regenerative Medicine, with the radiations conducted at B&L in our home institutions. The first portion of this project at UC Davis involves testing a space radiation countermeasure based on a biomimetic nanoparticle platform developed at the Lawrence Livermore National Laboratory, which we load with curcumin, a potent antioxidant and anti-inflammatory compound. We use low-passage MRC5 primary human fibroblasts as an in vitro cell culture model to validate these curcumin nanolipoprotein particles, or CNLPs, as both a radioprotector administered prior to radiation exposure or a radiomitigator administered afterwards. We identified 10 micrograms per mil as the optimum concentration for gamma ray exposures and began testing CNLPs for the types and energies of charged particles astronauts will be exposed to during an extended Mars mission. Cells are irradiated at the NASA Space Radiation Laboratory and evaluated using a variety of functional and genomic assays. The next portion of this work being done at Wake Forest includes evaluating CNLPs in a humanized mouse model in which human astronaut age CD34 positive hematopoietic stem cells are xenografted into immunodeficient mice and allowed to engraft for several months before the mice are shipped to Brookhaven for exposures at NSRL. 18 hours prior to radiation with a variety of low, intermediate, or high LET radiations, or the 5-ion mixed field GCR simulator, we administer CNLPs to some of the humanized mice via tail vein injection. Effects of space radiation and the countermeasure on different human blood lineages in the mice are evaluated by flow cytometry and functional and genomic assays. However, the most important endpoint of interest using this model is the induction of splenomegaly in human leukemiogenesis, which we've observed for mission-relevant doses of iron and oxygen ions, as well as for protons in the SIM-GCR sim. No human leukemias have been induced to date with gamma rays or observed in sham-irradiated control animals. The final portion of this project, being done at the University of Arizona, involves using an organ-on-a-chip microfluidic cell culture device they've developed to mimic the human GI tract and evaluate the impact of microbiome interactions on space radiation-induced responses. Using their human microbial crosstalk, or HUMIX device, their group has worked out protocols to successfully co-culture human primary intestinal epithelial cells with commensal bacteria long-term and evaluate the impacts of exposures delivered at NSRL. To confirm these results, we also radiate cohorts of wild-type C57 black 6J mice with and without CNLPs and collect multiple tissues, including blood and GI, 24 hours post-irradiation. These are processed and evaluated at Wake Forest, and I'm pleased to report promising initial results seen with CNLPs and their ability to significantly predict charged particle radiation-induced damage to the GI tract. I would like to acknowledge funding by the TRISH program and additional funding assistance for developing the CNLPs from Lawrence Livermore National Laboratory. We would also like to gratefully acknowledge the incredible assistance we received from NSRL and Brookhaven Laboratory Animal Facility staff, especially in 2020 during the coronavirus pandemic. Thank you, and if you have any questions about any portion of this project, feel free to contact us using the email addresses below.